Hello chaps and chapettes. Alright, today we're going to be looking at fission and fusion, and this is probably the first time we have this, but this is going to be specific to Cambridge International exams, and there's a reason for that. Different exam boards have different requirements on how far they need to go on topics, and for fission and fusion in Cambridge, they don't need to go in as much detail as the exam boards do. So rest assured, I will be doing some videos later on for AQA and EdXL and so on and so forth. But for now, we're just sticking with the Cambridge International because right now I have some students that need this desperately. So what they are going to need to know and what you will need to know is the difference between nuclear fission and fusion, and also understand how energy can be extracted from both of those processes. You should be able to draw a nuclear reactor. You don't necessarily need it, but it does help to have a good overall idea of what is used in that. And the challenge today is to figure out why people are actually afraid of nuclear reactors. It may seem quite obvious to your mind right now, but if you try to verbalize it, perhaps not. And hopefully you can let me know in the comments below what your thoughts are on that. So, jumping straight into it, what is fission and fusion? We'll start with fission because it's the older technology and one we actually have right now. Fission is the splitting apart of larger nuclei into smaller ones. So the classic example, taking some uranium, splitting it into smaller atoms there. I forget which ones they are. I will find out for you in a second. Fusion, of course, is the opposite of this. We're taking two small atoms and gluing them together into larger ones. And this is not the same as chemical bonding. Okay, we're not just taking a sodium and a chlorine and having them ionically bond. No, we're actually taking the nucleus of these atoms and fusing them together to make a larger nucleus. It's very different from what happens in chemistry and it's much, much more difficult. Typically you find fission in nuclear reactors, that's where we have it, and typically you find fusion in space, in stars. We do have fusion reactors here on Earth, but they are not very functional right now, in that they require more energy to run than you actually get out of them. So both of these processes can actually produce an enormous amount of energy. And we're going to have a look at a picture of a nuclear reactor now as a fission one and find out how exactly you can extract the energy from both of these processes. Because basically it's the same way, it's just that one small key part of it is different. So let's go into that now. Right, now I'm going to draw this in front of you and I'm going to regret that decision at some point during this video, because what I'm going to draw is not necessarily difficult, but it is relatively complex. So the first thing that you need to do for a nuclear reactor is you need to have some sort of fuel, and that looks something like this. There, and they are small rods. And that's going to be, in the case of a fission reactor, some uranium or something similar. Well, actually, it's mostly going to be uranium, which you hope to fission apart into smaller nuclei. And that's going to actually give you it's going to give you a lot of heat, essentially. Now, we do have these two other components to this. Okay. That one there as well, and there we go. Now these things are control rods, and what they are there to do is to slow down the rate at which your nuclear decay is happening inside. What's going to happen is you're going to kickstart a reaction here, a chain reaction, where the fuel rods have neutrons flying off inside them, and they're going to strike into uranium atoms inside the fuel rod itself. And as these uranium atoms break down, you're going to have further neutrons flying out, flying into other neutron atoms, and so on and so forth in a great big chain reaction. And this is going to get exponentially bigger as the reaction continues. You don't want that to happen, because if that happens, you've essentially got a nuclear bomb and everything goes kaboom. Oh, that's someone's driving outside the window. Okay. So this is the idea. Now, you want to have some way of extracting the energy out of this one. I've skipped a step, sorry. These control rods are there to actually reduce the number of neutrons that are flying past this thing. and that means that the reaction will slow down. So I'm just going to draw something else around this one, and you can see why we have that. So roughly speaking, we have this setup sitting inside a sealed up chamber. I'm just going to draw something off to the side there, okay? And what's going to happen is you're going to have water coming inside here, and that's going to extract the heat that comes off of this reaction here. So the heat comes off, water picks it up, and then heads out the other side as basically steam. So that's the idea there. Cool, now it's gone. Okay, so this is the idea. Now, honestly, this thing is going to be contained inside a core, thusly. Okay, well, actually, controller should be inside the core. And the water is going to come in, get warmed up by that graphite core usually, and it will come out as steam. So, water in, and hot water comes out. Okay, and that's a nuclear reactor setup. That's the inside of a nuclear reactor, or at least a fission reactor. So, just to recap, we have control rods, and we have fuel rods, core, usually graphite core, and we have water in, water out. So if this thing gets too hot, you push your control rods in to absorb more neutrons to slow down the reaction. If this thing gets too cold, then you pull them out to actually make the reaction happen a bit faster. In case you're wondering, this was Homer Simpson's job in The Simpsons, and if he had got it wrong, there would be a small nuclear explosion, and that would be the end of Springfield. This is the joke, in case you're wondering. Homer Simpson's not a terribly intelligent guy, and he was in charge of this massive nuclear reactor. So, there you go. There is more to this one. What we have next is this hot water going off to a steam turbine here. Okay. And then we have another chamber here, which I'll draw in a second, actually. And that loops around. Okay. There's a couple of extra features you can have on this one. Things like a small pressure chamber on there to absorb any changes in pressure. But this is generally the idea. Steam comes around, drives a steam turbine, which then sort of cools down. You know, I'm actually going to use a different color pen for this one, for the sort of cool down water. Extracting the energy out of that. And then here we have a coolant chamber. And what that is essentially has another wraparound water bit to cool down the water inside so you get too cool of water. If you have the water being too hot as it comes out and comes back into the reactor, then that's just going to be building up into steam faster and faster. The pressure's going to build up, and then this thing's got to explode, and that's Chernobyl. That's what happened there, where the temperature got way out of control, and then the pressure built up inside this whole thing, and boom, popped open. Now you do want to cool this stuff down, and you don't want to use fresh water, because this is going to be slightly radioactive water. I mean, it's sitting inside a nuclear reactor, so it will become ionizing at some point. So we don't want to have any of this escaping to the outside world. That's what this thing's for. This is then going to take some more water off to those great big massive cooling towers. Oh, hang on, that's completely off screen. Cooling towers. And that's going to be the big sort of, tower-shaped things with a little steam coming out of it. There's going to be a small pump driving water around here to cool things down. And that's going to be largely disconnected from the nuclear reactor, which means that you don't contaminate the surroundings as little as possible with any radioactive material. Now with Fukushima, a couple of years ago, the pump which was pumping water to this thing actually broke, which meant that the water spinning around here got hotter and hotter and hotter. And it was only thanks to the heroism of some very, very brave Japanese firefighters that it didn't go up in the end. What they essentially did was pointed their hoses at the nuclear reactor and just kept it cool until this pump could be fixed and the systems could take over again. And there you go. The only difference between this setup and a fusion reactor is that this bit is swapped out for a fusion chamber. And the way they do that is very, very complicated, so I'm not going to go into it in this video, particularly because you don't need to know it for GCSE. But essentially, take that bit out and then have the same setup. You have water coming in, heating up because of the fusion reactor, and then going around and driving a turbine, which generates electricity. As per every other power station on the planet, that's generally what happens. So, there we go. Gosh, this is a long video. Let's see if I can edit it down. Okay, so you should now know the difference between nuclear fission and fusion, and it's basically one is the reverse of the other. So you should also understand how the energy can be extracted from both of these processes. It's not very complex. It's basically caveman logic here. Make thing go hot, use hot thing to make steam, and therefore you can start generating power, get power generators off that. You should be able to draw a nuclear reactor as well. As I said, you shouldn't necessarily need it, but it's useful to know so you can explain the benefits of fission and fusion. And the challenge is to think about why people are afraid of nuclear reactors, because they are dangerous. No doubt about that, but they're not as dangerous or as scary as people make them out to be. So let me know in the comments below, what do you think? What are your thoughts on this one? And I'll catch you in the next video.